So I am Aaron Ames, as you can see on the projector. I'm at Texas A&M. I'm an assistant professor now. I've been there for 2 years. I'm the head of Amber Lab, which is just my lab under a different name because I think calling a lab like Ames Lab is kind of, egotistical. But it stands for Bipedal Experimental Robotics Lab. So everything that I do in my lab is in some way, shape, or form related to walking pretty much. It's kind of what I've become interested in. Always been interested in, but really made it a focus. So there's 3 of my students from the lab there. Brief background on me since I'm the MC. I got my PhD from Berkeley in 2006, my undergrad in 2001, and I did a 2-year postdoc at Caltech, and that's where I actually met Julia at Caltech. So I'm going to talk now. So what this is about, at a very high level, is trying to achieve human-like bipedal robotic walking. Now, this question was raised earlier today, and it's always raised, why do we want human-like bipedal robotic walking? And I think there's lots of answers to that. I think more than anything, at the intuitive level, people know they want robots to walk like them. There's just something very special about that. But there are actual ways you can justify it. And the interesting thing about this is this does not change from my job talk 2 years ago or 4 years or wherever. I mean, these have always been up there, and yet they're all very applicable and they don't change. So space exploration, that's really why we're here in some sense. If you can get robots to walk like humans, they can handle uneven terrain, they can go places where wheeled robots can't, they can find interesting things that wheeled robots can't. Military applications, exoskeleton designs, things like that, coupling basically robots with humans. Elderly assistance, making old people walk better, detecting when they fall. All those kind of things are very important applications if you understand walking. Rehabilitation of injured people, if you have knee surgery or bad back, how can you have mechanical assistance? If you understand walking, you could do that. And prosthetics, which is something else I'm really interested in. So creating that sort of bionic man. And these are actually a collection of robots that are out, and this is mine. Mine looks really pretty because it's not been built, so it looks better. SolidWorks rendering. Right? But these are a couple of Jesse Grizzle at Michigan, which does dynamic stability in 2D, but they're not 3D walkers, and they're under-actuated. And this is Asmo, which everybody's seen before. It's kind of the staple biped. Now, the important thing to point out about this is Asmo walks statically stable. And this is something, obviously, we're trying to get away from. And I think people intuitively knows what that means. Can anybody know what the Asmo walk is like?
Very robotic.
Very robotic. Can anybody mimic it?
You can stop moving at any point and stay.
Yeah, that's exactly what it is. If you stop moving at any point, you stay standing. So what do? Well, if you want to walk like Asmo, you try to keep your center of mass essentially over your feet at any point in time when you're walking. So here I can feel it. Okay, I'm still good. I'm still good. I'm still good. Right? That's pretty much how it walks. So it's statically stable because at any point I can stop. Now, dynamic stability is what we're shooting for, and this is where, when I'm taking a step, right, I could fall over. If I stop halfway through my swing, I just freeze, you're down. So it makes walking a lot more complicated when you try to do that. So again, human-like walking is the goal. How are we going to get there? Well, my sort of big picture game plan of all this stuff is to use human walking to motivate hybrid models and controllers. Okay, so there's 2 distinct things about getting walking in robots, aside from the hardware, which this talk will have nothing of hardware because I'm a control and software guy. But on the control and software side of things, the 2 things are, how do you mathematically model the system? And once you have that model, how do you implement controllers to make it do what you want? Okay, that's what it all boils down to. So the idea is to start from human walking to get robotic walking. And I'll explain a couple iterations of that. I'm actually going to talk about 2 different kind of control strategies because I kind of want to throw around 2 ideas to you. Some is the stuff that's well thought out, and the other stuff is this cutting edge stuff for me, which we'll get to on human-inspired control. First, a little bit of history, though, on dynamic walking. Dynamic walking first really began in the 80s with Tad McGeer. And what he discovered was that robots, or mechanical devices that are built like humans, legged robots, can walk without any actuation down shallow slopes. And not only that, but it looks remarkably human-like. So if you look here, this is McGeer himself in a video making this thing walk. And this is without any actuation. This is just initial condition, and letting it go. And if you see, it's remarkably human-like, right? And what this really says to me is that walking is somehow intrinsic to our mechanical design. And I think that's true. And human-like walking is intrinsic to our design. Okay? Now, from this, that's without control. So people have tried adding little bits of control here or there to achieve this walking on flat ground and varying slopes. So this is some work by actually an undergrad. So expectations high here. It passively walked down a slope just fine. And they added a little bit of actuation to it to get it to mimic this behavior on flat ground. And this is in 3D, and it looks remarkably good. Again, problem. This was all experimental. So basically, some guy that was really good at building stuff and tinkering did a great stuff. But at one point, they tweaked something the wrong way, and they could never get it walking again. So this doesn't show an inherent understanding of walking. Now, on the flip side, there's this sort of, this is a little bit old video, but this is walking that we understand from a mathematical perspective. It's dynamically stable and we understand it. But if you look at it, it's very robotic still, right? It's not natural. So we want to achieve the best of both worlds here. We want to get walking that we understand formally, but gives us natural walking that's repeatable and can work in a lot of varied circumstances. All right, so that's kind of your little history level lesson on walking, ignoring a lot of stuff that was out there, but I think that's a good big picture overview. So, again, the motivation is, if the fundamental mechanisms underlying walking can be understood, then we can get human-like walking. So how do we understand those mechanisms? Well, we're going to look to humans. Okay? So we're going to start with looking at efficient human walking. This could be in a variety of circumstances. I'm going to talk about walking straight on flat ground in this talk, but it could be turning left, turning right, going up and down slopes, going up and down stairs. And from this, you try to extract the mathematical structure of the model. Okay? And I'll explain that in this talk. Now, once you have that structure, you build controllers that make it walk. Now, that's tricky too. But the structure gives you a lot of insight into how you're going to build those controllers. You can do analysis and compare this walking back here and actually back to humans too. And then once you get good efficient walking, you can do things like prosthetic design, which I'm not going to talk about in this talk. All right? But you can build good prosthetics because you know how humans walk, so you can tie into it. So that's the big picture. So now on the modeling side of things, bipedal robots are naturally modeled by hybrid systems. So for some people, they're like, oh, I feel better now. There's going to be some math. For other people, they just want to turn their head off when they hear this. But you can't really get around the fact that the math behind robots is very complicated to understand. And that's a result of the fact that you have continuous dynamics when any number of contact points are in the ground. So if your foot's flat, you have some dynamics like this, leg swinging, right? If you have only your toe on the ground, you have some different dynamics, right? When your number of contact points change, you get a discrete jump in the velocity. So when your heel strikes the ground, you get an impact to the system. When you mix those two together, you get these hybrid dynamics. Okay? It's just unavoidable. Now, on the control side of things, we're going to talk a little bit about some controllers we've used in the past that are passivity-based, but we're also going to talk about some human-inspired controllers. I'm going to actually throw both at you to kind of give you a flavor of the different approaches. Because the passivity-based ones, although this is all my work that I'm talking about with passivity-based, it's a pretty accurate representation. In fact, it merges a lot of different pre-existing ideas. I would say that it's kind of a conglomeration of pre-existing ideas plus some new stuff. The human-inspired is kind of a totally different track, a different idea paradigm. And then we'll talk a little bit about how we can go to 3D. And we've actually found an effective way to do that pretty quickly. So I'll overview that really quickly. All right, so human data hybrid models. Again, getting our big picture back up here, what we have to start by doing is the modeling. So what I'm going to show you is, this is all actually quite new stuff, but it works surprisingly well, so I can talk about it in a short time window. What we're going to do is we're actually going to talk about how we went from a walking experiment, where humans performed walking. We took sensor data, and we fit functions to these different contact points. And I'll explain that a little bit better. And from this, you can determine the constraints enforced at any given time, which gives you uniquely these discrete phases of walking. You could call it discrete phases of walking, a domain breakdown, a hybrid, an automata. I mean, whatever you want to call it, it's sort of the discrete structure underlying walking. And we found this to be universal among all people, which is kind of shocking. I was surprised. Okay, but that's also very cool because it means if you want to build a robot, you use this, right? Why not? And the interesting thing is, in the literature, nobody had used this yet. So it's interesting. But all right, so what are we going to do? Well, I just went through this whole overview, so I'm going to skip this slide. But this was the 4 points that I talked about in words. I don't think you need to read them. All right. I always have to throw the slide up. I always will, till infinity, even on a high-level talk, because I think it's important to see the underlying math going behind this. It's just important to understand that there is some rigor underneath here. I'm not going to go through all the details of this. I'm not going to give you a detailed description of this tuple. But modeling robots, you have to start as a hybrid system. Okay? And what this amounts to kind of get this picture in your idea, is you start out with a graph, an oriented graph, which are nodes and edges. Okay? In this case, you have 4 nodes, 4 edges. On each node, you have a domain. This tells you how the continuous behavior can evolve, your phase space. Okay? You have a set of controls you can implement on each domain that can change. You have a set of guards. Now what the guards tell you is when you're going to make that transition. So the physical constraint on the system, so like the height of the foot would be a guard. And when that height's 0, you make a transition. A set of reset maps which tell you how your velocities change when you impact. Those are your impact equations. And finally, a control system on each domain which tells you what your vector field's doing. This is just a mathematical model of your system. So you break down the tuple, it's not that complicated, but it's important to understand that this intertwining between continuous and discrete makes walking different than a lot of control procedures that are out there that you have to do. Like with R2, there's none of this. You know, there's just continuous dynamics, unless you're switching between controllers. But all in all, there's not this interplay between discrete and continuous. And that changes the nature of the problem. All right. So now, going back to this whole notion of modeling, it turns out that the hybrid model is basically uniquely defined by this discrete structure down here. But there's something important to understand, and it doesn't automatically come out. Okay? It actually has to be chosen. It's a design decision that fundamentally affects the walking. So in the case of this, it's called the compass gait biped. In case you have a biped with straight legs, no feet, not a very realistic model, you can only have one, and it turns out. Basically, you have continuous dynamics, and then the foot strikes, right? If you add knees to it, you basically can get 2 if you have knee lock. Knee unlocked, knee locked. Okay? But when you start adding more degrees of freedom to the model, you get more choices. So if you have something that's more realistic, knees and feet, all of a sudden you could have a 4-domain model, a 5-domain model. There's actually, how many possibilities? A lot. So there's a total of probably like, I don't know, a lot of domains that are possible. And between all those possible domains, there's transitions. So things kind of blow up in complexity. For example, with this model, you could have a discrete domain where the toe is on the ground and the heel like this. You could also have one where both your heels are just on the ground. Right? That's allowed from a mathematical perspective. But of course, when we walk, we never have a period where both our heels are on the ground with nothing else. It's not very, right? So we ignore that. But the question is, how do you pick those domains we actually want? So again, now we're going to go to people. So,
for a period of walking before you switch to the other leg?
Yeah, it's for one step. And then you switch legs, and then you perform it again. So it's understood there that you actually have periodic walking, meaning your left and your right leg act the same. All right, so let's talk about this experiment. What we did really quickly was, we did this little motion capture. This gives you an idea of the limited scope. It wasn't a very long little platform. And we walked 10 times or 12 times, I guess, just taking a couple steps, trying to walk at a natural speed. There was no constraints, just walk at a natural speed to you. Okay? And we tried talking to people to kind of distract them from the walking so it wouldn't be forced and things like that. But that's what our motion capture looks like. And so I just saw the guy looking bored in the background. Yeah, everyone can see him. That's a graduate student at Berkeley. He looks very uninterested with my walking. And then we get this kind of data at 480 hertz. We get this sampling, and this is the raw data we're dealing with. You see, even now we're dropping a lot of sensors. We throw our drop sensors to the origin. So things are in and out even on this short experiment. This was like a $25,000 motion capture system, so this isn't cheap stuff either. But there's obviously some uncertainty involved in doing this stuff. All right, so now the interesting thing we found, and this is where all the idea generation probably came from, is we needed to determine when the heel and the toe were on the ground at any given foot or combination thereof, because that determines this hybrid model. The problem is, if you look at this data, when that data is actually 0, meaning the heel's on the ground, is not clear, right? I mean, the heel kind of does this dip here, and then there's this thing here, and what's actually 0? You could try thresholding it, but that wouldn't be good because you could ignore some stuff or have too much stuff. Same with the toe. So we're trying to find a good automated way of picking these transition points. We could have gone through by hand and said, well, kind of right there. We're on an automated way. And looking at these, and just one day I was like, you know what? Those just look like really simple functions. Let's fit those simple functions between some constants. And then, so in the case of the heel, it looks like a Gaussian. So let's fit a Gaussian along with 2 constants on either side and find the minimum error between those fits. And then when we're in the constant part of this, we're on the ground. And we did that, and you see, even so, we're kind of ignoring the sensor behavior here. We're saying that this is on the ground and dips below it, right? And that, by the way, is when the heel strikes, the sensor deforms a little bit, jumps down and up, right? Because they're not rigidly attached. So by fitting these simple functions, we can actually determine when the heel and the toe are on the ground. Now that seems like a trivial thing, and I explained it too long. But the reason I did that is because this is the basic idea generation behind what I'm going to talk about later, and that's human-inspired control. That humans seem to, when they walk, these simple functions seems to come out. In this case, it was a 4th-order polynomial, you know, and it's not quite as good. But this is a fit of like 0.99 almost, coefficient of correlation. So it's really good fits. Anyways, enough about that. Because what you can do is then you can say, okay, now I have these fits which tell me when I transition from the foot being on the ground, or the heel being on the ground and lifting, and I can look at when the constraints are enforced. So the constraint for left toe is enforced here, left heel's there. Then I could drop it down and figure out which ones are constrained at any given time, and get this domain breakdown, this discrete structure, which says, okay, here I have 2 contact points on the stance leg. Here I have 1 on the toe. Here I have 2, double support, and here I have 3. Okay? And once we get this domain breakdown, or this discrete structure, or automaton, or whatever you want to call it. The interesting thing is, out of everybody that participated in the experiment, everyone had exactly the same discrete structure, except for one person, who actually had surgery like a couple weeks prior to the experiment. And she actually had one domain that was different, this one. This one, her toe was off the ground, which is kind of interesting because she had kidney surgery, which is kind of her walk back a little bit. So that it tells you that there's some interesting fundamental things going on here. All right. Now, how do we transition this to robots? Okay, I'm not going to go through a lot of details on all the formal modeling, but let's say we have a 3D robot, okay, looking like this. And with this robot comes a mass distribution and lengths and all the things you have with a robot that are constrained, okay? What you can do is start with this human-inspired walking, all right? And now you can tailor it to the robot. So for example, for the robot, you might want to say the knee locks. Now I'm going to talk about knee being locked for one robot and knee being unlocked. It turns out that humans don't lock their knees, okay? There's never actually a point when the knee really stops moving. And I'll explain that a little bit later. But if you wanted to have knee lock, because it does save some energy in the system, you could add a knee lock, but keep the same contact points, okay? And then you've made this discrete structure specific to the robot. And then you can get a hybrid system from this. Basically, it's automatic. I'm not going to go through the details, but the graph comes from this guy here. Underline it. The domain comes from all the configurations on any given domain structure. The vector fields come from again, the Lagrangians for the system. The impact equations come from the constraints, and you get a model. Okay? Bunch of dorky math stuff that we don't need to go into. All right, so now let's go back and see if we can get robotic walking. All right? Starting with our big picture, I'm going to talk about first an approach for 2D walking, sort of that's within the scope of traditional walking. This would be, people have seen the Pratt stuff, this kind of falls in this envelope of using basic passivity-based ideas and building some complexity from it. Okay? So what we do is start with the sagittal restriction of the robot. And in this case, that just means we take out the lean from side to side. And so you have to, whenever you do walking, what sort of my paradigm has been, and this is what I built up with lots of models, is you start doing 2D walking, and then you extend to 3D. And if you can get 2D walking, you can pretty much automatically extend to 3D. With some caveats, obviously. All right, so once you have this model then, what you need to do is, and this is where this discrete structure plays such a big role, is you have to look at the domains where you have full actuation and under actuation, and decide which controller to implement based on those domains. Okay, so this domain structure dictates your controllers. Now, I'm going to talk just a little bit about the ideas going by here. I'm going to be skipping through this a little bit faster because it's a little bit more technical than I think is needed for this talk. But I'm just going to throw the big ideas, so ignore all the math if you want and listen to what I'm saying. But the first idea that a lot of people have worked with robots is taking this idea of McGear, where you have this passive walking, right? And then they try to translate that to flat ground. So the passive walking down slopes, you can translate to flat ground by basically modifying the potential energy. Basically what you're doing is gravity's pulling you down. If you're on a slope, it's like this. If you're on flat ground, it's like this. So you rotate gravity like this, and you're walking like this, and you're walking down the slope, right? So this actually can give walking, and this was some of our older stuff here, where we could do this successfully with full actuation on walkers with just knees. And you see that we get pretty reasonable looking walking. Okay, I mean it's not great, but it's got some nice dynamic feel to it. Okay, again, in no ways is this realistic in terms of implementation, because we're actuating the ankles, which don't even have feet, right, and the knees and everything. So it's not a good place to start, but and knee lock. We have knee lock. Okay. Now, kind of keep this mental picture in your mind, because the walking that we get at the end, I think you'll see there's been a big jump, okay, in the way the walking looks that as we've evolved. Also, keep these images in mind. This is your limit cycle, which tells you have walking. It means that walking is periodic. When you get a closed loop in the phase space, it means you return where you started. So keep in mind the simplicity of this limit cycle, and as we build up the complexity, it will start growing. Okay. It'll start getting crazier. Now you can do this controlled symmetries in the case of under actuation too, and you can also do some spring damper controllers, and you can also do some lambda zeroing controllers. So basically what we did is we took that controlled symmetries that I showed you. That's kind of our essential controller. And then we did here what a lot of people do, throw little controllers on top of that to get what you want. So this lambda zeroing controller is simply, if you have feet on your biped now, you need the heel to lift. What do? Well, you can look at the normal force to the ground on the heel, and you can try to zero it. If you zero that through the control, the heel will lift. So we implemented this as trying to get this whole heel lift behavior. So this is another controller we threw onto there. So once we have these controllers, one more controller. This just kind of gives you a feel of all the hacks that have gone into, that usually go into walking, because this is pretty representative, as the people in the walking group would say, right? We have one more control we had to throw on because our toe was scuffing. So we had to do like an anti-gravity thing, where when the toe gets near the ground, we lift up the heel, and right? You guys are smiling because you're like, we've seen these before, right? So this is what walking has been about. And you know, we had different ideas, but in the end, this is what it's been about. So this will be nice when we contrast it with the human-inspired. But although we haven't completely removed these things, we're getting closer. So then once you have that, you have this discrete structure, and you're going to do what people have seen before. You're going to go through the domains and pick the controllers based on all the behavior you want to have, right? So in this domain, we have full actuation. So we're going to do this controlled symmetries where we're walking down a slope virtually. We're going to do a spring damper at the ankle to keep the foot from rotating. And we're going to do a scuffing prevention because the toe's coming forward and we don't want it to hit. So we take those three controllers and we pop it there, right? Then we look at the next domain. And on this domain, we're going to do the same things we did before, plus we're going to add in the lambda zeroing. Basically, because on this domain, we know that in the next domain, the heel has to be up. So what are we going to try to do? We're going to try to pop the heel up on this domain, right? So the important thing about this is that this discrete structure does kind of dictate control design, and that will always be universal. So knowing it is very important, and that's why getting it from humans is very important. The flip side is that there's way too much hackishness going on here, right? It's kind of like, okay, if something else bad happens, you throw some other controller on there to prevent it, and pretty soon you have 20 controllers that you're playing around with, and you have no idea what any of them mean anymore. And you can't change behaviors because the controllers you had were specific to the behavior. So that's kind of what people do. I'm not going to go through the rest, but you get the idea. So doing this, we could get 2D walking, though. You see the limit cycle's added a little bit more complexity here, but we get this kind of walking. How do people rate this on the human-like scale? It's okay, right? Nah. It's not bad, but it's not like, wow, that's awesome, right? And I'm going to point out this too. This is before we started really caring about these things. This is bad. -40, this is bad. We've improved it since. This was a little bit older movie for a talk that I gave. Like, this was CDC. Like, this was only a year and a half ago, though, that we were doing this stuff. So we've come a ways, actually. But we didn't really care about physical implementation here really yet, right? A lot of velocities going on. I don't even know what the torques were, but
that's also not real time. That's why it looks so.
That's choppiness is not real time. It's actually slowing down at the impacts. But don't worry about it. The point is, it's not great. All right, but at the time it was very good. All right, so now let's go to 3D with this, and this is an important idea that I think is still has a lot of merit, and coupled with some other stuff we're doing. But the idea is, once you have 2D walking, and this was actually what got me back into walking after a while, was the idea that you can use geometric reduction to decouple the system. So what you want to do is say, okay, I have my forward walking and it's great. I want to get side-to-side motion. I don't want to fall over. So what I want to do is decouple my system and have my forward motion not be affected by my side-to-side and vice versa. So the way to do this is actually utilize reduction in geometry. I'm not going to talk at all about this, but I'm going to give you the game plan. The game plan is you start with 3D walking. You have a sagittal restriction to get to 2D walking. And then you can do your control law, your favorite control law, whatever it is, to get to stable 2D walking. Now, the first control law, what we do is we shape the energy of the system, kind of like we did with controlled symmetries, to get to this shaped system where we can apply reduction. And basically we have some theorems out there that say that the system can be decoupled from certain initial conditions, meaning that this forward motion will not be affected by the side-to-side motion. Okay? So that's what we know. These two systems are now related, the 3D and the 2D. And finally, all you have to do is one more control law to push the system to those initial conditions where it's decoupled, and you get 3D walking. So it's kind of just a really high level. There's lots of technical theorems and math and stuff underlying this, but we've done this with lots of models, and it works surprisingly effectively. So the end result is that given 2D walking, we can sort of automatically generate 3D walking. Of course, we can only do this on the fully actuated domains, but we put a bunch of local controllers on the under-actuated, and I'm not going to go into all that. But the end result of all this is we do get 3D walking. So I'll just show you the walking. It's not bad. This is actually, is this real time now? It looks like it's real time.
Yeah, but the feet aren't actually bouncing. That's just an error in the animation.
Yeah, I didn't notice that. It looks better, though. It looks better. And let's see, do I have any other movies here linked? I should. This is kind of what it looks like with regard to the actual 2D walking, to kind of put it in a little bit of perspective without a fancy SolidWorks model. It's got kind of the same, I mean, it looks a lot the same, basically. Okay? Because we've decoupled the dynamics. But we do have walking in 3D here. Now, the interesting thing is you can actually compare the limit cycles and show that the 3D walking is slightly different from the 2D walking, but not much. Meaning we've achieved this decoupling. All right. So that was the state of the art for us 4 or 5 months ago. Okay? I mean, not bad, but not amazing yet. Not what I really wanted. Okay? So I'm just going to give a brief overview of the next generation here, which is really what I'm interested in doing. This is all we're doing now. But it's all very new, so I don't want to go through a ton of details. But basically, go back here for a second and remember that the way we got our hybrid models, our human-inspired models, was looking at human data, finding these canonical functions that fit it, to use this to get this constraint structure, to get this hybrid model. Okay? So we went from human data to model through canonical functions. All right? Now let's do the same thing for controllers. But first, again, recall from the previous thing, basically, if you have a biped and you have this discrete structure, you uniquely get a hybrid model. Okay? So we have a hybrid model from human data and a robot. You need the Lagrangian for the robot, you know, the dynamics of the robot. But the next idea is let's actually see if we can find canonical functions, not just to determine this model, but to determine the controllers. And so what I don't mean here is just trajectory tracking the angles of the human. What I mean is trying to find combinations of angles of the human, you know, configurations of the human that seem to follow very simple functions that are intrinsic to walking. And from this, we're going to use this to get walking. Okay? So I'll explain this in just one slide because it pretty much tells you the story. All right? And the one slide I'll spend a little bit of time on. And basically, so if you look at this kind of complicated thing, these are some of the things that we've considered. So this is actually, we have a torso now and all these things. But let's take the knee angle. In this case, we're actually looking at a straight up angle. So we want to develop controllers. We look at the angle behavior of the knee over time. Now the blue one is the non-stance or the swing, and the red one is the stance. Okay? So what is going on there when you just look at those functions? Let's see if we can intuit a little bit about walking, kind of get behind this process. All right, that's the human. The data for the human is the circles. Ignore the red and blue lines right now. What's going on there? Think about knee. Think about the behavior of the knees. When the human's walking, okay, put your leg down. Think about you swinging your leg forward. What's happening? You kind of relax. Just kind of swing it, right? You let your momentum carry over. That's pretty much a Gaussian. So what we found is Gaussians seem to describe the free swinging behavior of people. A Gaussian describes the heel when it swings, and a Gaussian also describes the knee when it swings. Okay? So we follow a Gaussian when we're swinging. Now what's happening here? That's the stance leg. All right? So think about this. When you're walking, your leg hits, your foot hits, and then you go forward. All right? What does that behavior look like? See if anybody can pull it out. Not the students in the lab. It actually makes a lot of sense when you just sit there and look at it for a second. Think about if you've had a basic control class, undergraduate control. That's it. Looks like an impulse response. Remember impulse responses? Right? You hit a system, what does it do? A spring damper system, basically. What does it do? Spring damper. Kind of jostles and falls in. Okay? A second order system response simply means the impulse response of a spring damper system. That's what it looks like it's following. Why? Well, think about it. When you land your leg on your knee, what's going to happen? Well, all of a sudden you have all this weight. Right? So your muscles are going to tense for a second to prevent you from collapsing. Then they're going to kind of push off a little bit. Right? So they're going to take that impact and bring it back. Spring damper. So you basically can fit a second order response to this. The solution to a second order system. And we find a really good fit. So this is kind of the underlying idea that you find these simple functions and you understand what they mean, okay? And these are the canonical functions associated with walking. So another one that's really interesting is the slope constraints. So what we're doing now is we're looking at the angle between the ankle and the hip. So this is a really important angle because a lot of what people have done with walking is idealized a biped as simply being a pendulum, an inverted pendulum that you're swinging forward. So basically that angle is capturing that angle of the inverted pendulum. All right? So what does this say? Well, when you're on your stance leg, it's basically a constant. Right? So what does that mean? Well, when I'm swinging forward, I'm bringing my whole body forward as a constant. Right? I'm not trying to do anything fancy. I mean, whatever my knee's doing, I'm just bringing it forward. And then what about here? Well, on this one, it looks like a sinusoid. Because why? Well, you're just kind of sinusoidally swinging your leg again. So free things tend to follow combinations of exponentials, right? Gaussian is a combination of exponential. Sinusoid is a combination of exponential. Constrained things tend to be a little bit more interesting. So we can fit these two functions. Again, we get really good fits. All right, so the last one is the foot behavior. And you can tell what's still a work in progress, right? I'm going to own that. We have some ideas. We got things working, but this is still not clear yet. How the foot behavior happens. Okay, so we've just been playing around with kind of keeping constants, and we're playing around. The good thing is the behavior of the swing foot doesn't really seem to affect walking all that much. So it's not a huge deal. But these are the big ones that we found so far. So 4 canonical controllers for walking. Okay, and now what we can do is we can go through our domain structure and implement those controllers on certain domains like I showed you with the last model. Just pick and choose. Okay? And the end, one more thing that's interesting is people might say, well, that was one person, right? We looked at all the people for the walking, and unfortunately the data itself isn't in here, but they all were good fits, right, Matt? All the data would fit with all these functions. So the point is it seems like humans seem to, so here's the knee, decaying exponential fits, second order response fits. All the people seem to have that sort of behavior. with pretty high fits. Now, again, as the weight changes or the height changes, the parameters of those functions change, but the underlying functions are the same. So with a robot, you can't expect it to have exactly the trajectory that the human would have, but you can modify the parameters of the function for the robot to get the walking. Okay, same with all the other things we found. Very good fits. Okay? Which tells me, I mean, this is sort of going towards this universal functions for walking. All right. So an end result of this is we actually get stable walking again. So let me go through here. Oop, that's not the one I wanted. All right, that's the same one. But all right, so this is our state-of-the-art walking, and it's a lot better. Real-time walking. Let my computer settle down. So if you kind of think back to the walking you saw, the other movies you saw, I think there's a big difference. It almost looks like we just taking a human and tracking its trajectories, right? I mean, you could think that would be motion capture data almost, right? But we're actually implementing these controllers on a robotic model. And little things that I was excited about with this were like the knee behavior. You see that it does this knee catch that humans seem to do. And I think the knee catch is more than just a response, but actually when you hit here, it makes a lot of sense for efficiency that you let your leg break a little bit to kind of let your center of mass come forward just through natural dynamics. And then once it's on the other side, you're going to pop it up. So that's actually kind of what's happening as it falls through here, if you see the timing with it. So this is kind of the most recent walking we have. Now, we don't have 3D walking yet because we haven't done it yet, but this is what it might look like if it cheated, meaning this is 2D walking on a 3D SolidWorks model. I'm going to own up to the cheating, but I think it will look like this anyways. I'm selling it if you're buying. No, I think we can get something similar to this. We could either do what we did before, but what I really want to do is go back and look at canonical functions for 3D walking too, and stick to that sort of idea, that philosophy. But anyways, that's a meaningless movie compared. It's the same thing as the other one, but it looks cool. All right. Now, there's some powerful things that you can actually do now that you've built human data from all this, or you've come from humans with all this. I'm doing fine on time. So one of the things that comes to mind is you can actually start comparing walking back to humans and say how human-like is the walking. So as a first approximation of this, I'll give you an approach. There's better approaches you can use. Once we really sort out those canonical universal functions, you can actually compare to those directly. But before we do that, what we can do is start looking at the humans again. And what we can do is compute the amount of time spent on each of these domains. Okay? So in this case, 65% of the gait was spent with the foot flat on the ground and the other leg swinging. We can take all those percentages and we just get a weighted graph. Okay? We can find the weighted graph that best fits all that collection of weighted graphs. Okay? And this is a little bit less intuitive than it seems. We're actually using a bona fide distance metric on graphs and doing a bunch of math, but whatever. Long story short, basically you're finding the average of all these. Okay? And that is your optimum walking cycle. Meaning what that is the best fit on the amount of time you spend in each domain based on the data. And we found this kind of breakdown. Okay? And if you watch people walk, I think this is actually pretty accurate. If you try to catch the period of time when the foot's flat and the toes on the ground with people, it's hard to catch. Believe me, I watch people walk way too much when I'm like going around. People probably think I'm creepy, like looking at everyone's feet, you know? But if you watch it, it's pretty fast. This is definitely where you spend most of your time, 60% of your gait. You spend about 25 to 30 or 20 to 30% of your gait in double support. That actually agrees with pre-existing studies that have been done. But nobody's ever actually broken down walking to these phases before that we could find. They've only done, because usually people in biomechanics haven't thought in the robotic modeling frame of mind, so they haven't thought to look for these things. But once we have this optimum walking cycle, we can just say, well, let's see how human-like we are. What we'll do is compare the amount of time we spend in each domain to this thing. It's a little bit more elaborate than that because, again, most of the models in the literature don't have these domains. In fact, none of them do except for ours. So you have to actually compare models with different domains. I found a metric to do that called the cut distance. None of that really matters. But in the end, what you can do is say, okay, how human-like am I? If you have a robot, you get a weighted graph, whatever that graph is, and you just look at the distance between the weighted graph of your robot and the optimum one you found from the human data. Now you could imagine actually, this is something that could be built upon. Like we did an experiment with 9 or 10 subjects. You could do another experiment and get 10 more and start working it together and building a metric based on data, because this is a data-based metric. But this gives us a cost. And the important thing here too is if you're building a robot, you could take these functions that we have to get walking, but then you could actually optimize with respect to this cost to make the walking even better than it is already. And not only that, but you could apply this cost function instead of like the specific cost of transport or things like that to pre-existing models. So right now there's a lot of cost functions around. You might have seen them. There's torque squared, there's specific cost of transport. There's lots of things you can do, but I don't think any of those quite tie right into the human-like nature of walking. So this is kind of an alternative approach to that. All right, getting into the results, we did this comparison between the people, between the model we presented in this paper, and between pre-existing models in the literature. Okay? So now, let's start with the people. So in the people, we just compared each person to this optimal. And you notice there's one person that's really big cost. That's actually me, just because I'm special. And even the graphs have to know. All right. It's because I actually have a bad back. And a pretty bad back, like herniated discs, pinched nerve. It's a mess in there. And the point is, it was picking up on that. It picked up on that difference from everyone else in my walking. Okay, everyone else was pretty uniform, right? About half the distance, half the cost of me. And the other interesting thing is that this person here was the person that I visually identified as having the best walking. And that was because he was somebody that practices like martial arts and all this stuff. So his walking was like fluid butter, It was really smooth. And he's light. He only weighs like 140 pounds, and he's all like muscle. So it was like very nice walking. And that pulled out as the lowest cost by quite a bit. So I was really shocked when I saw these results. I was pleasantly surprised, let's say, that it really pulled those things out automatically. Now this is the model we presented today, the cost of the walking for our model. You see that even though we tracked those human functions, even though, in fact, the person we ended up tracking was Fred, which is S4. So, because we did this not in a timed fashion, but kind of multi-threading, the person who plots we used was 4, which is probably not smart because he had some of the higher costs. But we still didn't even hit his cost, which actually is a good thing because it's telling you that on the robot we can't do quite as good as the human could, right? Which is expected. But we still get a lower cost than anything that's around so far. And these things were actually a result of 2 optimization papers. Very top-level people in optimization, and they basically try to do all these things and optimize models of walking. Okay? And interestingly enough, out of all these models, this is the one that the people in the paper said had the best, most human-like walking. So, and we pulled it out as the lowest cost. And again, we didn't plan any of that. So, again, this says that something's going on here. And the walking from this paper looked worse than the walking from this paper. So it actually made sense that those models would be different. So there's clearly a sort of a line. It's kind of like 0.5. Below is good, above is bad, if you wanted to draw it like that. So trying to get a robot between 0.5 would be my rough sort of out of nowhere figure. But that's kind of the idea. All right, so the conclusion is, what do? We took the first steps, no pun intended, all right, towards closing the loop on robotic walking. I can't even say that because it's meant to be, it's not even clever. But what we really tried to do is go from human data around and close the loop, right? So we used human walking data to motivate the mathematical model. Then we also constructed control laws that also attempted to be anthropomorphic in nature. And then we also provided this cost of comparison. Okay, so those are kind of the big things that we're going at. So where are we going from here? Well, more of this, I guess. This was actually a slide I meant to take out, but because I talked about it in this talk. That was a previous talk where I was talking about future work, and now we've done it. So one thing I'm interested in is neurocontrol. I've been talking to some people who are neuroscientists, and what's really interesting about all this stuff with walking, and the people I've been talking to all day will hear some repetition here, but it seems like humans break up walking into 2 parts of their brain, or not even parts of their body. It seems like when you're walking straight or doing some constant steady state behavior, your walking is actually controlled at the level of the spinal cord. So neurons in your spinal cord control those walking. When you switch gaits, you actually have a signal from your brain that kind of initiates a gait switch. And the reason why they started detecting this was actually they did experiments with cats in like the 70s or 80s. And what they did, they severed the spinal cord of the cat. So no signals going from the brain to the back legs. Then they put the cat on a treadmill, and it could still walk without any signals, which says that the lower level walking seems to be intrinsic. And this is actually consistent with this philosophy of simple functions guiding walking. Because if you're only controlling walking at the level of your spinal cord, you can't have really complex stuff going on there, right? So somehow we've programmed in our spinal cord these basic things. So the idea is if you understand that, you can actually use neurocontrol really effectively. One thing you do is directly tie into a monkey, because you can cut into its brain and use that. But you can even imagine things like EEG. Like even for space exploration, this would make a lot of sense, right? You want to have some astronaut controlling the biped, right? You don't want him to sit there with a remote, switch left, switch right. You want to give him a live video feed, hook a cap up to his head, and he's walking around the surface of Mars. Now, he'd have to be on Mars because of time delays, but you get the picture. But for the moon, this might be more possible. If you walk slow, of course, you can't walk on the moon because the walking changes, so you'd have to do moonwalking. And all right, stuff's complicated, but it sounds really cool. But I think there's a lot of potential here. And basically, the idea is you use neural signals to switch between motion primitives. And so what you do is you create a template of controllers, like walking straight, turning left, turning right, and then you switch between them on neurocontrol type signals. Okay? And then you can apply them to the robot. So that's one place that I want to go right now. Another place is prosthetic devices. I'm not going to talk about this slide, but obviously if you understand how humans walk, you can put those controllers on prosthetic devices and hook them up with people. Then you can imagine doing something more complex, like actually neural-controlled prosthetic devices, using these switching between motion primitives. So all this stuff kind of ties together in some sort of golden thread, right? And I think that's it. Yeah, that's all my slides. And I also want to build something, but my purpose of being here is hoping that NASA can help with that, because you guys are better at building stuff than me. That's for sure, since I've never built anything. You're probably better. But so that's where we've come, where we're going. So I'm sure I have time for questions. I actually ran through that fairly quickly. So thank you for listening.
So
My grad student interrupting my applause. Go for it. Oh no, it wasn't him. I thought it was Matt. Go ahead.
If you're walking over, just arbitrary terrain, how do you think the selection of canonical functions seems like that's going to break down?
I would say two things. First, if the disturbances in the terrain are small, then what you're going to do is rely on the robustness of your current controller.
Okay.
So that will be able to handle perturbations, because you want to make it as robust as possible. And so if you hit a little rock, you don't want to switch between templates of controllers, right? That should be kind of automatic, right? Humans don't think when they hit, a carpet from a wood floor, they just falls right in. Now, if the terrain is so rough that you're outside of that domain, in that case, I would say you do have to switch controllers. And if it's really that big that there's big boulders sitting there, just like a human, right? At some point, you can walk on ground. If it's grassy, if it's uneven. At some point, if you start seeing rocks, what do? You have to look down, right? It's at that point that you have to go into a separate controller, which would probably be a sort of a foot, looking at how humans do foot placement. And what I would do is I would get a template I would watch people doing foot placement. Not where they're placing their foot exactly, but the procedures behind it. And build controllers based on a foot placement template, right? And then switch to that if the terrain gets so bad that you're outside of that robustness window. So that's the way. So there's kind of, that's the advantage to doing this formally, though, is that I think there's some formal leveraging you can do coupled with the templates. It's not like saying everything should be, because if you want a human to turn 1 degree, you don't want to go to another experiment with 1 degree, right? You want to have kind of turn at 45 degrees. Everything else in the middle should be able to be done formally with robustness.
So I was shocked that nobody else has formulated that. It's simply brilliant. But
Thank you.
So what about upper body dynamics and the importance of that in that cost function and all the other things?
That's a good question. I think that upper body dynamics plays more the role of adding robustness, right? rather than actually achieving the behaviors themselves. So I think it's important, but my focus was on understanding the walking first. So we have like a torso that we're stabilizing, so we know we could put an upper body on there. And we have, right now we have all the mass of an entire upper body of a person actually centered on that torso. But I think adding in those controllers later would be something to look at. And basically I'd like to look at how humans try to, how they use their arms. Because obviously the way to kind of, it's like when people walk on tightropes, right? There's a lot of arm movement. In fact, they add an extension, which kind of tells you that arm movement is more tied to stability, right? Side-to-side stability, than being intrinsic to walking. Because if you have a nice flat ground with nothing in the way, you can walk like this, you can walk like this, it won't even change how you walk, right? So I think a torso is being adding stability and allowing you to achieve tasks. But I don't think it really destroys walking if your walking is robust. You agree?
Yeah.
All right. I thought it was coming from Matt there. Yeah, no problem.
In your plant, your robot plant, what is a joint? Is it a torque source, a velocity source, a position? How do you represent a joint in your model?
How do we represent? I mean, we feed torques to the joints. Torques, yeah. We're doing torque-based control. Just because we're just starting. I mean, again, we're starting at the level of dynamics here. Yeah, and so we have x dot equals BU, BU coming in the Lagrangian, right? Yeah, So
I thought that was really good. I like the idea of decomposing into sort of fundamental control pieces. But one thing I noticed is that you're primarily looking at sort of normal adult walking, right?
Yeah.
So it'd be interesting to look at maybe infants learning how to walk and see if I suspect you would find something like a slow accumulation from maybe one or two simple control functions, and then you add on another one, how it interacts, and see how that would grow.
That would be very cool. Yeah, that would be very cool. I think that, I mean, I'd love to do that actually, if we can sort these out, because it would be cool to see when an infant first walks. Even it'd be awesome to see this entire process, right? Starting when they can't walk, right? And they try to take a step or two. And are they actually kind of hitting those functions a little bit, right? And as they start to learn to take a couple steps, are they starting to zoom in on those functions? Are they learning those functions, right? And that would be super cool to see. And then which one do they learn first? Just the simple walking in a straight line of flat ground, probably, right? And then as they get bigger, they probably start to add templates to their controllers, like turn left and right, and
like an accumulation of more
elaborate, right? And that'd be actually a great way to start with robots, is trying to go to some child behavioral analysis people, wherever they live, and be like, what is the order that infants learn things? Do they learn to just walk? Because we know they kind of learn to walk straight first, right? But after that, what do? Do they start turning next? Do they start running next? Running, right? I think it's actually, I don't know what it is. Yeah, I mean, so this would be great. I mean, I don't know. I mean, I wish I had the money and the resources and the time to study all these avenues in this big coherent picture of, universal human movement of some sort kind of thing. But, I got to start small. So, but it is important to mention that in the experiment we performed, the ages range from 19 to 77. The heights ranged from somewhere 5'4" to 6'3" or something, right? The weights were from 130 pounds-ish to 200. So, I mean, it was not like we had, and there were four females and 6 males. So it wasn't like we just took, 22-year-old college kids that are engineering and ran them all. So, yeah, which is hard. I mean, finding a variety of people for an experiment was actually challenging. We were like calling people, do you have a friend that's a girl that can come over here right now and run this experiment? So, yeah.
Once you have your template curves,
yeah.
How are you implementing that in the controller?
Just input-output linearization. So, I mean, standard nonlinear control is basically you make those curves your desired functions, virtual output. And then you zero that virtual output with input-output linearization control. So it's basically what Jesse Grizzle does, but with different functions. I mean, that's what he does with all his walking. The movie you saw, the robotic walker, we just use different functions, but the same general control ideas. Yeah. So it's pretty much the only way to do nonlinear control I mean, there's not a lot of options for nonlinear control that works in a really robust, good fashion. That's pretty much it. So.
What's the difference also between yours and his?
The functions, a lot of things actually. First, the functions we're following, being human inspired. He just does polynomials, random degrees, and picking and constraining the functions makes a huge difference in the end. Also, we're doing 4 domains. He's never done more than 1. So we do this human inspired domain breakdown. And in addition, we do mixed under actuation, full actuation. He only does under actuation. We also do single and double support. He only does single support. Those are some of the lists. I have a ton of respect for Jesse. I think he laid the groundwork for doing these kind of nonlinear control in bipeds, but there's definitely a lot of differences. But it's definitely compatible with what he's doing. The ideas are compatible. It's just, instead of just, the idea is really kind of like, all right, a control theorist would think, let's just pick polynomials of any degree and we'll just optimize them later after we get walking, right? Which makes a lot of sense. But, instead coming and saying, no, we have to pick the functions that we're picking first, and then we'll do the control. Based on humans is kind of a difference, paradigm shift over to, human inspired.
Identifying the physics behind getting some of those functions. For example, you have a certain curve for the passive knee as it swings, and modeling out the dampers or springs that are happening in the knee. So
you mean starting at the level of human musculature movement and forcing, or just
more abstracted
dynamics of pendulums and things like that?
Exactly.
Yeah, I mean, that would be actually worth thinking about. Like this whole idea that
At the end of the day, it's kind of what he was touching on, is that how you can extend it to other things that you haven't programmed for.
Yeah, I agree. I mean, I think, like, for example, this notion that Gaussians are followed. Why Gaussians? Why would some statistical measure be the things that seem to follow? For both the heel and the knee, it's a little weird. So is there something intrinsic about the free swinging mechanical systems that they tend to follow Gaussians in their solutions? I mean, that's kind of what I'm postulating. And maybe you could prove it. Like for a simple double pendulum, let that thing swing, and maybe you would see that you could actually prove that there's Gaussians that come out with free swinging behavior with spring damper systems or something, right? Which would be kind of cool, So.
Yeah, it seems like the trajectories that we've arrived at, I mean, we didn't pick those because we like them, we pick them because they're optimizing something.
Yeah.
It seems like the question is, what are they the optimal solution of?
Exactly.
And once we know what that is, it seems like that's how then we can generalize to other situations.
Yeah,
I mean, it seems like that might be critical to making like a piece of robotic hardware actually walk, as opposed to making a human body walk. Yeah,
I think there's something to that. I mean, and this is part of my original motivation for all these ideas, was that people right now, they optimize, they'll just, they get something to work, right? Optimize, minimize torque, which makes a lot of sense in robotics because you have a finite amount of torque and you want to make it smaller, so you optimize it, right? But oftentimes this is done with too few parameters and under the assumption that that's what humans would do. And I don't think humans optimize torque. I think it's a combination of factors. And so understanding that combination of factors is what this is about. So I think that humans balance 3 things when they walk, for example. I think their cost function breaks down to 3. This is all just anecdotal. I mean, there's nothing to support this, but it would be torque, or how much energy they're burning, stability, and speed. So you want to go far in little energy. That's kind of the specific cost of transport. But the last thing that isn't included in that, and that I think is very important, is stability. Not fall over. So what's interesting is we had that 77-year-old perform this experiment, and the walking looked different. I mean, it still fit within this envelope, but it was a little bit slower and more concerted. And what's really happening, I think, as you get older, is you start prioritizing different things more. So she's going to prioritize stability, because if she falls over, it's much worse. While we had a 19-year-old guy that was 6'3", he looked like he was going to fall over the whole time. He looked like it. Why? Because if he falls over, so what, right? Nothing's going to happen. So he prioritizes, speed and minimum energy over stability. So I think as people age too, and this is another thing with kids, right? It's the other end of the spectrum. Kids prioritize stability almost 0. They don't care. They can bounce off walls at that age, right? So they have a 0 stability, and they have maybe, for them, it's just going forward. It's not even torque. It's probably not even, they don't care that they're going forward with less efficiency. They just want to go forward. So they want to travel far, right? So those cost functions, I think, change around as you get older and younger and all these kind of things.
It'd be interesting to collect the same set of data, but disturb like the mass distribution of the human. Like, put a backpack on or have them carry dumbbells out like
right.
this. You can just see if the functions still agree with the data. Because,
yeah.
Because again, like the making a robot walk is not making a human body walk.
Right.
So if you can just wiggle the standard deviation of the Gaussian that's controlling the knee, then great.
Mm-hmm.
It'd be interesting to see if it holds up. Just,
yeah. I mean, I think.
Serving the human system.
Sure. No. I mean, and we have some data for that because we did think about trying to check that. We had people walk backwards. We haven't done that comparison yet, but we'd like to compare walking backwards to forwards and if everything breaks down and where does it change. We had people jump up and down, But I think in the end, I mean, I think what really has to happen to answer all these questions from the infants to whatever is automating this entire process. So basically, you press go with some sensors on, and it automatically determine everything. And then you could start really answering these questions and get into the bottom of it, right? But as such, though, this took 2 days to collect data on 10 people walking in a straight line, right? It takes a half an hour to put on all the sensors, and you have to do the data, and then that doesn't mention the processing afterwards. And so right now, on a limited, being a professor with grad students kind of deal without, a huge workforce behind you and a lot of money behind you, you're limited in the things you can do.
So you mentioned something about the automation. You mentioned before that the kind of the state of the art was you kind of arbitrarily pick how many discrete or domains you want, and then you kind of slap controllers on as you go.
Yeah.
Now you kind of automated the first step of that, which was to find the domains, and then. But now it seems like you moved the problem to finding relationships between variables and what it is that you want to model and capture. Have you put any thought into how you're going to take that, finding the relationship between the variables automatically? Or
now that's a little bit trickier, right? Because what we had to do here was look at a bunch of relationships. I don't know how many things we looked at, like a lot.
Kind of exploring that.
Yeah, we're still exploring. We're not totally done. Like we're sure on like the knee and the leg slope. Those seem like they're done deals. But of course, that was just for walking straight. If we're going upstairs, those might not hold anymore because some of the things we looked at were not good. You could not find good functions to follow them. So. That's kind of this, right now it's a process of looking at all these things and then saying in my mind, that's a simple function, that's not. Let's track that, right? Then there's other functions that are simple that we couldn't track. I didn't mention this yet, but things that, if you have functions that depend on length too much, it can screw up the tracking because you get singularities. And so there is still a little bit of an art to this part of it. Now, but I could at least see automating it at some point. If you can find the collection of things, sort of take all collections of possible combinations that look good. And then see which of those you can fit a function with 5 or less parameters. Call that a universal function then. And if you can do this along all data sets, so you could kind of see a decision diagram start coming together on how to do this. It's going to be more complex than what we did before, but you could see how you might have an algorithm to kind of run through this and check to find the simple representations. Out of those, you pull them out, and then you can just say, okay, I'm going to try all combinations of those functions as controllers on all these domains and check to see if you get walking. I mean, it's possible. I'm not saying it's anything that's easy at all. Like this first step was much easier to automate. That I think you could automate just straight up. But it's possible. And the main point there is that the stuff we were doing before, where the current state of the art, where you kind of just willy-nilly pick, what they do is they add more domains. Because like, well, maybe we forgot this one, so let's add a domain there and here, and you get this huge transition diagram, and then you slap controllers, and oh, this isn't working, slap another one. That's just for one walking behavior. I don't think there's any way that will ever be automated, right? And I think if we can't automate achieving walking, we're never going to make it as versatile as we want it to be. Because the whole point of bipedal walking, its benefit is versatility over wheeled things, right? So we have to get there. Yeah. All right. Thank you.